Hello dear audiences, this is the part 5 of Probability and Statistics for Engineers, and this is Mohammad Momenzadeh, the presenter of this course. So previously we discussed about the permutation and some counting axioms and methods were studied. So today we want to discuss about the combination and the continuation of that counting techniques. So before that we reach to the topics and the contents that we have it. Indeed, the contents and topics can be seen in the next slide. So we will discuss about the combination and probability and axioms today. I want to just emphasize about something which is too important in my side of view. So the things that I want to talk about it is a technique of accounting. Sometimes we have a complicated question that can be simplified with the simple methods. It's important to understand the question clearly and try to find a similarity between the question to answer that type of the question. Let us take a look at one example before that we continue our course, and this example is totally related to the previous lecture. So what is the example? So this is the example that we have it. At the question they ask to find the different cases of 5-letter words that can be formed using the letter from A to J, means total 10 letters, such that each word has at least one letter repeated. So let us take a look at the question clearly. As I said it before, understanding the question is the most important part of the question. They said that at least one letter repeated over there. So it's totally different from the cases that we studied before. I want to emphasize about these things. As much as you solve the question and examples, you get better and better in this case. Most of the question has a simple techniques or tricks, but it's important to understand the question clearly and then try for that one. There is no way to stuck in any question. Let us take a look over here. If we have 5 letter, means that we have a 5 location. Let me just put it over here, 3, 4 and 5 location over there. And if we just use that 10 letters for each part, means that each of that places can be occupied by 10 letters. So if I put 10 letters over there, 10 letters for the next one, so means that the repetition over here is allowed. I just allowed all possible repetition, so it's 10 letter more and 10 letter over here. So the total cases that can we consider over here is 10 to the power of 5, or 10 times 10 times 10, 5 times. So 10 times 5 is a cases with the repetition. So this case, these cases that we talk about it is with repetition. So the question is about that if the repetition is not allowed, what is the cases over there? If the repetition is not allowed, then again we have 5 places for 5 letters, and we can put 10 possibility for the first one, 9 possibility for the second one, 8 for the next one, and 7 for the next, and 6 for the last. As you can see, when one letter is omitted from the repetition, then we have the less value over there. By the other words, we have 10 objects, so it's a permutation of 10 objects which placed on 5 locations. So the result will be 10 factorial. Let me just write it over here. It's 10 factorial over 10 minus 5 factorial, 10 minus 5 factorial, and 10 minus 5 is 5, so it will be 5 factorial at the denominator, and 10 factorial over 5 factorial. As you can see, it's equal to that value, means that we have 10 factorial at the numerator, so 10 times 9 times so on up to, let me just put 5 in the middle, so 5 and 4 and so on again up to 1, and if I just divide this value by 5 factorial, which is equal to 5 times 4 times 1, means that this part will be 5 factorial. So if I divide it by 5 factorial, then the result will be as the same as the thing that we have it over there, means that it's gonna be 10 times 9 times 8 and up to 5, so up to 6 indeed. So this is the value that we have it over here, and by multiplying them you can use the multiplicative rule directly to write them. So in this case we have the cases that we don't have a repetition. So I mean, this is the without repetition. So the question is about that what is the subtraction of this to 1, means that if I subtract all cases 10 to the power of 5, if I subtract the repetition cases from them, means that if I subtract this permutation of 10 objects in 5 places, what is the result of that one? So for sure this is all cases with repetition and without repetition, and if I remove the cases that we have no repetition, so the result of that one will be the cases that at least we have 1 repetition. So this is the answer for that question. As you can see over here, if we wanted to solve that question directly, at least we should look over there for 2 repetition, for 3 repetition, for 4 repetition, and 5 repetition as well. And it's too difficult to solve that one, means that you should calculate all that cases and add them together. But with this simple techniques, the subtraction of all cases without repetition from the cases that the repetition is allowed, we can find the cases that at least we have 1 repetition, and we solve this question. As you can see, some difficult question can be simplified easily by using the simple techniques. So it's important to understand, again I emphasize about that, it's important to understand the question, and as much as you solve more example, you get expert in this type of the things. So at least I taught this course for I have taught this course for around 10 years, and so I solve a lot of questions in this duration. If you want to get this experiment, you need to solve more example about it. So in the next step we have this mixed permutation theorem, and let us take a look at the theorem. The number of distinct permutation of n things, of which n1 are of one kind, n2 of a second kind, and nk of kth kind, it's gonna be equal to this value. So you have 2 examples over here, but let us take a look at the another example that I want to make it over here. Let us consider some books that we shelf it in a library. So for instance, let us take a look at these books. So I just put the shape of that books over here. Assume that we have 5 historical books, 4 math books, and 3 biological books, and we want to shelf them in 1 row. So in how many ways we can shelf them? That's a question. If it was distinguished books over there, and they were not important for us to put the history, what type of the history book at the beginning or second. If we can distinguish between the books of the history and the book of the mathematics or biology separately, then it was the combination, it was a permutation of these objects, and simply we could answer this question that okay, we have 5, 4, and 3 together, it becomes 12, and we have 12 factorial. That is the combination, different combination of them. But over here, as you can see, if I just put the history book at the beginning, let us just at the end, I should sketch it after a long time that I found something. So if I have this book, for example, the history, and I put the another history close to that one, and even if I swap their places, what do I mean swapping their places? Means that if I interchange their place of these two history book, then that type of the cases should be counted as the same. Means that nothing gonna be changed when the history book is interchanged, the places of them are interchanged. So because of that, we have 12 cases totally. We said that, okay, this is 12 factorial of the cases, I mean all permutation for these 12 books, and we divide the similarity over there. We have 5 factorial for the similarity of history book, 4 factorial for the math books, and 3 factorial for the biological books. And this is the meaning of that mixed permutation. So it means that if we have n things of objects and n1 of them are in a one kind, so n1 over here based on this example is the historical book, which is equal to 5. n2 of them are in a second kind. This n2 can be considered as a math books, that is equal to 4 over there. And the third one, n3 over there, nk, we have 3 cases, so n3, or the third kind of the books over there are the biological books, that is equal to 3. And the result of all possible permutation for this case is equal to n factorial over n1 factorial, n2 factorial, up to nk factorial. So by using this concept, you can make a lot of examples, and it can be done for the cases that is more complicated. Let me just give you one example of the case that that was my favorite example in this case. Let us take a look at this example. Let us have a grid over here, and let me just put some grids over here. So let me just divide this rectangle to some parts and put some vertical line as well. And if I just repeatedly put this one and make some grids like this, now the question is as follow. So we have one robots or one machine over here. Let us assume that the machine is located on this point. Let me just put one machine or one car or one vehicle. So this is a vehicle, and it starts to travel from a point A, and it wants to go to the point B, which is located on the other side of an edge. So this machine can only travel to the right or up. Means that this is only 2 navigation that we can consider it for the movement of that car. Right now this question can be considered totally practical over here. For the robotic things, we have several questions like this. So the question is about that in how many ways the car or that vehicle can travel from point A to the point B with that rules that the car can only move to the right or can go up. For example, one of that movement is like this. It can be go to the right, then up, and again up, then right, then up, then right, and right again to reach to the point B. And as you can see, I just use this movement to reach from a point A to the point B. The question is about that in how many ways we can travel from a point A to the point B. This is that type of the question that at the beginning the question looks totally difficult, but by using some small techniques you can simplify that question, and at the end it's gonna be totally easy. So let us take a look at that question. For solving this question, I try to put a code for any travel. Let us put a code, for example, 1 for moving to the right, and a code 0 for moving top to the up. So means that, for example, this movement from A to B can be written like this journey, this travel. Let me just write it. The travel that I mentioned it over there is given by these codes right now. So it's going to the right at the beginning, so I will put 1. Then it's going up, so it means we have 0, and again up. At the next step it's going up again, so we have one more up, which is 0 again. Then it's going to the right, which is 1. Then it's going up again, it's 0, and we have 3 right as well, so it will be 1, 1 and 1. So this is the sample of that traveling from a point A to the point B. I want to ask you if you understand how can we count all possible traveling with just simply putting this method of coding for movement. So if you just take a look precisely to that question, then you will find out that if we travel from another way, we should have 3 0 inside of it, because 3 times it should go up. And we need only 5 cases to go right, because there is 5 grids or 5 meshes to go to the right side. It means that if I want to write another travel over there, for example, let me just use this traveling, this method of movement, 1 0 0 0 and 1 1 1 1 and 1. So as you can see, for the green travel, let me just put it by green T, we have 3 0 at the beginning, 0 0 0. Then we have 5 1, so because 5 times is moved to the right, 1 2 3 4 and 5 times is moved to the right. So this shows one thing, that any travel means that any travel from a point A to the point B, any travel can be somehow corresponded with one array of digits that contains 5 1 and 3 0. So right now the question is totally easy, because we can count the number of these things based on a previous discussion. All cases that we have it over here, it looks like a books. We have 5 historical books and 3 mathematic books. It looks like that you want to shelf them closely. So there are n1 kind over here, n1 kind over here is equal to 3, and n2 kind of the things is equal to the number of the second kind is equal to 5. So all possible permutation for that case will be 8 factorial over 3 factorial over 5 factorial. So easily you found it. That was a complicated question that we simplify it easily to find a solution for that one. And as you can see, with that techniques we simplify the question and solve it.
So as we promised previously, we discussed about the combination right now. And as you can see over here, this is the definition of the combination. And if you have n objects and we want to discuss about the r cases over there, or r places, then the result of combination of r out of n can be written by this symbol or simply by the braces, and it will be n factorial over n minus r factorial times r factorial. So the differences between the combination and permutation can be seen in this example that I sketched at the right side of the screen. So you can see that the sample space over here contains 3 elements, A, B, C, and we discuss about all subsets of a size 1. Over here, the subset of a size 1 can be considered as A, B, C, and as you can see, the combination of 1 out of 3 based on this definition can be seen as a 3, the resulted as a 3. In a subset of size 2, the situation is more clear. So as you can see, all subset of size 2 is written over here. There is no differences between the subset of A and B, and the subset of B and A. However, at the permutation, we should make a distinguish between these two things. By the another words, when we discuss about the combination, the places of the objects are not important. We just think about the situation as a group of elements, as a set of the element. The best way to represent the combination is using the subset or the set of the elements to discuss about them. So, for instance, in this example, we have 4 mathematicians, 6 computer scientists, and we want to find a committee. When we discuss about the committees, means that in the committees, the place of the people are not important. For instance, if I have a committee of size 3 that consists 2 mathematicians and 1 computer scientist, then it doesn't matter that the computer scientist is coming first and the couple of the mathematician comes second, or vice versa. So the important thing is about the committee, the group of a people. So when we use this type of the words, means committees, group of a people, or the set, then we should use the combination. And as you can see, we choose 2 person out of 4 mathematicians and also 4 computer scientists over there out of 6 cases, and this is the result, which is equal to 90. It's not a bad idea to take a look at the Newton binomial expansion, and over there you can see the result of this combination. Indeed, this combination is used over there very well. So let us take a look at that concept. So as you remember from the high school, we have a Pascal triangle, and how can we construct this triangle? Indeed, we started by 1, and at the edge of this triangle, if we consider one triangle over here, so we can see this is the triangle. At the edge of this triangle, we have 1. As you can see, there is 1 at the edge of that one. In each side of triangle we have 1. So this is the Pascal triangle, and how can we interpret it? What is the usage of that one? As you can see, the 1 at the beginning can be seen as a plus b to the power of 0. So this triangle is constructed to calculate the coefficient of a plus b to the power of n. For the second one, 1 times a plus 1 times b is equal to a plus b to the power of 1. Indeed, it's determined the coefficient of a and b in an expression that we have it. And the second one, the next step shows the famous and familiar formula for the second degree, means that 1a squared. Then I reduce the power 1 times, and I will write a instead of that one, and I add to the power of b, a times b, and 1 times b squared. So this coefficient 1 is a coefficient of a squared, 2 is a coefficient of ab, and 1 is a coefficient of b squared. The result determine a plus b square. And for the cube case, we have the next line as well, means that we have 1 times a cube. Right now I will start it by a cube, then plus 3 times a square. I reduce the exponent of a 1 times and add to the exponent of b, and plus 3 times a, again I reduce the exponent of a and add to the exponent of b. It's gonna be b squared plus 1 times b cube, and the result of that one determined a plus b cube. So it will be a plus b cube. But for the remaining part, if we want to write the whole exponent and the coefficient in one formula, we have a Newton expansion. Indeed, the Newton is a person who discovered in this formula for the general cases that we have a plus b to the power of n. If I just use a summation to determine the formula, then I have this summation: k is equal to 0 up to n. I have this expansion over here, and it will be a combination of k out of n, means that these numbers that we have it in a Pascal triangle is k out of n, the combination of k out of n, a to the power of k, that is increased, or we can write it by n minus k to have the similar formula that we have it at the top, b to the power of k. So in this way we can determine the a plus b to the power of n, the binomial formula for that case. If I expand the formula, it's as follow, means that it is started with the k equal to 0, so I have 0 out of n, so this is the first coefficient, 0 out of n, a to the power of n, as we had it before. The next expression will be 1 out of n, 1 out of n, this is the next coefficient in a Pascal triangle, and a to the power of, I reduce the exponent 1 times, n minus 1, and I add it to the exponent of b, so b plus 2 out of n, the next one will be 2 out of n, and then we have also a to the power of n minus 2. I reduce the exponent of a again 1 times more, and I add to the exponent of b, and I will write it by b square, and it's going forward this expansion up to the end. At the end of the day we have n out of n, this is the last number over there, n out of n, b to the power of n, and because of this n to the power of n out of n, this expansion, and 0 out of n, you can see that 0 out of n is equal to 1, and n out of n, the combination of n out of n, is equal to 1, and because of that we have this 1 at the side of this triangle in a Pascal triangle. So what is the relation between this Pascal triangle and Newton expansion to our discussion, the combination? As you can see, we have a combination over there. So let us put a equal to 1 and b equal to 1, then we can see these things. So as you can see in this picture, we have the binomial expansion, as I said it before, a plus b to the power of n, and I replace a and b by 1. If I just replace a and b by 1, then the result of that expansion by simple substitution will be as follow. Instead of a, if I put 1, and instead of b, if I put 1, 1 plus 1 will be 2, the result will be 2 to the power of n. At the right side, all the expression that has an exponent becomes 1, so we have the combination of 0 out of n, 1 out of n, 2 out of n, up to n out of n. And as you can see, based on a definition that we talk about it, all subset of a size 0 can be determined by the combination of 0 out of n. All subset of size 1 is 1 out of n, 2 out of n, and so on. So the addition of all subset of size 0 up to size n determine all subset of S. And based on the information that you had it in high school, all subsets of S, if S is given by 1, 2, 3 up to n, if we have n element inside of our sample space, then these things determine the subset of S. Indeed, if A is a subset of S, and S is determined by 1, 2 up to n, with some small techniques you can find all subset of S. If A is a subset of S, as I said it, there is 2 cases for a number 1. If I just consider the number 1, there is 2 cases. One, does exist in a subset, or does not exist inside of that subset. There is 2 possible situation over here. So for a number 1, we have 2 cases. One case is that the number 1 does exist over there. One case is that the number 1 does not exist in that subset. For a number 2, we have 2 cases as well with the same logic. For a number 3 as well, for a number n as well. So as you can see, by the multiplicative rule, all cases for subset of S can be considered as 2 to the power of n. And as you can see, all subset of S is equal to all subset of size 0, all subset of size 1, up to all subset of size n. So in this case, we can find all subset of the given set. After a brief explanation about the combination and permutation, it's a time to discuss about the first axiom of the probability of an event. So this definition is the most important part of the discussion in a probability. Indeed, with using these axioms, we can determine the probability of any event. So let us take a look at the definition or that axiom. Suppose that an experiment has associated with in a sample space S. Probability P is a numerical value function that assigns a number PA to every event A so that the following axioms hold. The first one is about that the probability of an event should be positive, or it's greater than equal to 0. The probability of whole space or the sample space is equal to 1, and if A1 and A2 up to AK, for instance, is a sequence of mutually exclusive events, means that there is no intersection between them, then the probability of their union is as the same as the summation of their probability. It seems that this axioms is too difficult to discuss about it, but let us consider one simple example, and with that example everything can be clear. So first of all, assume that we have a coin, and this coin is tossed by some person, and when the coin is tossed, we have two cases. One case is given the tail, and the another case is a head part. So the sample space that we have it over here is given by this shape then. So this is our sample space S, and it contains all possible outcomes. So we have tail, 1 point, 1 sample point, and the another sample point is a head, and we have this case. So the S or the sample space is given by the set that contains tail and head. So this is the situation, this is the statistical experiment that we have it. Right now I just collect a part of this sample space as a set A. This is gonna be the event. As you remember that we define the event A as a subset of a sample space, and I want to calculate the probability of that event. Indeed, I want to know that what type of the number should be assigned for this event to say that the probability of A is equal to that number. Assume that this coin is homogeneous and is unbiased, means that the possibility of occurring tail and head are equal. So for this reason I just define the another set as well. Let me call that one as B. And right now I can see that A has no intersection by B, means that the intersection of A and B is equal to empty set. There is no intersection between A and B. With that condition, A and B are mutually exclusive. So I can say that A and B as the two events are mutually exclusive. There is no, or they are disjoint, or there is no intersection between them. So based on a third axiom that I have it over here, if A and B are mutually exclusive, and also we have the union of them over there, the union of them means that A union by B, as you can see, the union of these two sets is equal to the sample space. So based on a third axiom that I talk about it, I can say that the probability of their union, A union by B, is equal to the summation of their probability, means that it's equal to the probability of the first one, probability of A, plus probability of B. So probability of A plus probability of B. But the union of A and B, as I said, it is equal to the to the S, the sample space. This one is a sample space. And again, based on the second axiom that I have it, the probability of S or sample space is equal to 1. So the left side of this equation is equal to 1, and the right side of that one is as the same, means that it's equal to the probability of A
plus probability of B. It's remained in their places. But we said that the coin is unbiased, means that the possibility of occurring the head and tail are as the same, means that the probability of A is equal to the probability of B. And because of that, I can use this condition, this actually unbiased condition that I set it over there, and write on the right side that the 2 times of probability of A. So in this way, the right side of that expression can be written as a 2 probability of A. At the end of the day, I found the probability of A. The probability of A is equal to 1 over 2. As you can see, by using the axioms, I calculate the probability of getting tail, for instance, when the coin is totally unbiased, or it's not actually, it's homogeneous, the coin is homogeneous. But calculating the probability with this method is too difficult. We need more practical methods to calculate it. I just calculate the probability of some simple events over here to show that how can we use the axiom of the probability. So the important part over here is about the probability of a number. From this axiom, we realize that the probability of an event is a number between 0 and 1, and if it's equal to 0 means that that probability, that event is impossible, and if it's equal to 1, then it's gonna be the sure possibility, and it's a whole space, the probability of whole space. And the another important part over here is about the case that we have it. So if we have a sequence of mutually exclusive events, means that we have, for example, this is A1, this is A2, there is no intersection between them. As you can see, they are mutually exclusive. If it's A1, A2, and it's going on up to A infinity even. So we have the sequence of that type of the events over here. Let us limit ourselves to the n cases. If you have a disjoint actually events over there, then the probability of their union means that if I want to calculate the probability of A1 union by A2 union by A3 union by AN, if I have the union of this disjoint event, then the probability of their union is as the same as summation of their probability, means that it's equal to the probability of the first one, means that probability of A1 plus probability of A2 plus probability of A3, and it's going forward up to the probability of AN. And this is the meaning of the axiom, the first axiom of the probability. But to find the practical way to calculate it, we should take a look at the next slide. So at this slide, you can see that if an experiment can result in any one of n, capital N, different equally likely outcomes, it's important to emphasize about this one that the cases have equal chances to occur, different equally likely outcomes. It's important to emphasize about these things. I mean that the cases that we talk about, it has the same chances to be occurred, and if exactly n of these outcomes correspond to event A, then the probability of event A is the small n over the big N. So what does it mean? I mean, how can we use this theorem that is coming out from the axioms in a similar ways that I discuss about that experiment? How can we use it? Indeed, we should find the cases that contains inside of that event. We should count it very well, the elements of that event. Then by dividing the number of the elements inside of the events by whole elements of the sample space, we can find the probability. Let us take a look at one example. So this is the example that I made it right now. Assume that a box contains 3 blue, 2 green, and 4 red balls
consider one box, and inside of the box I have 3 blue balls. So let me just put 3 blue balls over there, and we have 2 green. So let me just put 2 green, 2 green, and more 4 reds. We need 4 reds, so 1 and 2 and 3 and 4 reds. And we draw the balls from that box. So we draw 3, indeed we draw 3 balls over there, as you can see in the question. So we draw 3 balls. So we want to know that what is the probability of getting 2 red and 1 blue. First of all, we should take a look on the situation very well. Based on a given information, the order of the balls that I took it out is not important. I mean, it doesn't matter that which one is a first, which one is a second, which one is a last. So we just have a group or committee or set of the balls over here, and it's not important. Their places are not important. So we should use the combination to calculate the number of the elements over here. Our sample space contains all possible outcomes, means that if I assume a sample space over here, if I just name it a sample space, then the sample space contains all possible outcomes. For example, this sample space contains the blue, blue, blue. So this is one case that all of the balls that comes out are blue. So the another one is blue, green, red, for example. The another one is red, red, red. We have all cases in our sample space, and I want to know that how many cases do we have in our sample space, how many of them are there. That's the question. That's the first thing that you should understand. It means that when you have any probability question, the first thing is understanding very well the question. The second one is counting the elements of a sample space and counting the elements of that event. So to count the elements of sample space, I draw 3 actually balls out of 1, 2, 3, 4, 5, 6, 7, 8, 9. Totally we have 9 balls in our box, and we just draw 3 of them. So means that the number of the sample space, if I want to write the number of the sample space, the number of sample space will be the combination of 3 out of 9, because their places are not important. It looks like a group of elements. It looks like a actually a committee, or the grouping data, or a set. And 3 out of 9, the combination of 3 out of 9 will be 9 factorial, 3 factorial because of a number at the bottom, and 9 minus 3 is 6, so 6 factorial. And if I cancel the multiplication of 9 factorial and 6 factorial, then I have 9 times 8 times 7 times 6 factorial. That is cancelled with the 6 at the bottom, and we have 3 factorial over there, which is 3 times 2. So 3 times 2, we have it at the denominator. After cancelling the elements, we have 3, and this one becomes 4. So always the number should be a complete number. We will never have the fraction, the complete fraction over there. So it's going to be 28 times 3, 28 times 3. So this is the number of the elements inside of the sample space. And the case that I want to find it, the event that I have it, is 2 red and 1 blue, means that I'm looking for 2 reds and 1 blue. So I should choose 2 reds out of 4 cases, and I should multiply that one by 1 cases out of the blue one, which is 3 blue over there. So 2 out of 4 and 1 out of 3. 2 out of 4 is 4 factorial over 2 factorial over 2 factorial again. 2 factorial, and the subtraction of 2 out of 4 is 2, so we have 2 factorial. And for the next one, we have 3 factorial. 1 factorial at the denominator, and the differences between 3 and 1 is 2, so we have
2 factorial as well in a denominator. So 4 factorial over 2 factorial it's gonna be 6, and 3 factorial over 2 factorial will be 3, so we have 6 times 3. So right now the probability of that event means that the probability of A is equal to the favorite cases for that event, means that 6 times 3 over the number of the elements inside of the sample space, because there are all have the same chances to be occurred, there is no differences between them, so it will be 28 times 3, and this 3 will be cancelled again, and we have 3 over 14. 3 over 14. This is the probability. This is a probability of an event of getting 2 red and 1 blue balls out of this box. So I will finish the lecture today, and I hope that you understood the concept, and thank you for your attention.